Good evening, everyone. This is Karthik Reddy Beereddy, a senior site reliability engineer specializing in cloud native platform modernization and event driven architecture. Over the past decade, my work has focused on building resilient, scalable, and self healing systems on Azure Kubernetes services with an emphasis on automation, observability, and zero downtime operations. My journey in SRE has been about transforming large traditional systems into high availability, real time platform using open source technologies and modern DevOps practices. Today, I'll be sharing insights from the recent work on Kubernetes native platform modernization. So, before getting into the topic, I would like to share how the current industry has been evolving. So, over the last decade, we have seen cloud architecture evolve from the static VMs to dynamic containerized workloads that can respond to change in a real time. Kubernetes has become the backbone of this transformation, not just as a container orchestrator, but as an enabler of declarative automation, resilience, and portability. What's exciting today is how teams are rethinking reliability, shifting from reactive firefighting to proactive engineering, where the platform itself anticipates and recovers from failure. This evaluation is not just technical, it's cultural. It's about empowering developers, automating recovery, and bridging observability with operations. So what we're going to learn today. So one is the battle tested design patterns, real world deployment insights, and comprehensive pattern catalog. In the battle tested design patterns, we discover proven patterns for building self-healing cloud native streaming systems that ensure throughput consistency and availability at scale. In the real world deployment insight, we gain critical insights from high volume event stream deployments, processing mission critical data in production environment. Whereas in comprehensive pattern catalog, we acquire concrete tactics and a robust toolkit for designing streamlining pipelines that withstand failure and recover gracefully. So let's get into the architecting for resilient streaming foundation. Resilient streaming systems demands an architecture built to withstand the unpredictable nature of distributed environments such as architecture or simultaneously uphold three properties which are critical. One is throughput, consistency, and availability. So the throughput, which sustain high volume message processing without performance degradation, whereas consistency, which preserve data integrity and message order despite failures. And in the availability, which ensure continuous service operation even amidst component failures. These critical properties embody the cap theorem trade-offs inherent in designing any cloud native streaming systems. So let's discuss about the Reddy streams, which is replayable event log and observe downstream failures and coordinate consumer groups. So in the replayable event log, the Reddy stream maintains an append only log, enabling deterministic event play. Messages persist with unique IDs and timestamps, precisely reconstructing sequence after failure. In the observed downstream failures, this resilient buffer observes temporary downstream failures, preventing data loss, automating backpressure management, safeguards against memory exhaust during extended outages. And the coordinate consumer groups, which built-in consumer group management ensures load distribution and automatic failover. Field consumers resume processing from their last acknowledged positions, maintaining. So on top of this, so we in current world the platform has been modernized in large enterprises, especially those with decades of legacy systems. The modernization is not it's not just about containerization; it's about transforming entire delivery models from moving from nightly batcher and static APIs to event-driven, scalable services that can handle millions of requests per day. So the challenge often lies in maintaining service level clusters while ensuring compliance and security. That's where reliability engineering principle intersects with Kubernetes native design. So let's discuss about the circuit breakers, which is mitigating cascading failures. So there are three states: closed state, open state, half open state. In the closed state, requests flow normally while the system monitor error rates and response times for anomalies. In the open state, when failure thresholds are exceeded, the circuit opens, causing requests to fail immediately. This prevents resource exhaustion and cascading failures. Half open state. So this periodic health checks are conducted to assess service recovery. Traffic is gradually restored as downstream service stabilize. So let's discuss about the reliable event replay for system consistency. So in this event replay, we have three aspects. One is preserve message order, restore system state efficiently, ensure idempotent processing. So preserve message order where employ partition keys and sequence numbers to ensure deterministic message ordering during replay. This is crucial for maintaining state consistency across distributed systems. In the restore system state efficiency, where harness event sourcing patterns combined with snapshots and incremental replay, so quickly restore system state after failures. Minimize recovery time while ensuring data idempotent process. Design message handlers to be idempotent, allowing safe replay of duplicate messages without side effects. This guarantees exactly one semantics in distributed environment. So now let's discuss about the Kubernetes microservices partitioning and data scaling and service mesh integration. So in the event of partitioning, use this partitioning to distribute load among consumers while preserving message order. When we talk about these event-driven architectures, one of the most overlooked yet critical component, the event hub. So the event hub partitioning plays a major role in parallelism and ordering. Each partition acts as an independent commit log, allowing multiple consumers to process events concurrently while preserving order with that partition. The key is finding the right balance between the partition count and consumer scalability. In one of our implementations, we tune partition counts dynamically based on throughput trends. For example, billing events peaking during business hours or synchronous results after nightly batches. This approach helped maintain high ingestion rates without hitting throttling limits of over provisioning resources. From a site reliability engineering perspective, partitioning is not just about performance, it's about resilience. It isolates failure domains. If one consumer group or partition experiences an act, the others continue processing seamlessly. In short, if it well planned, partitioning gives you both scalability and fault isolation, the twin pillars of reliability in any streaming system. The second one when with the scaling is a Kubernetes event-driven auto-scaling, which is traditional auto-scaling in Kubernetes is often metric-driven, like CPU, memory, or requested. But in event-driven systems, the real indicator of load is queue, depth, or event length. This is where KEDA shines. So KEDA allows you to scale workloads based on external metrics. In our case, the event of consumer lag. So when the queue backlog increases, new pods are automatically spawned as the queue drains. They gracefully scale up. This dynamic responsiveness eliminates idle computer and reduce costs while maintaining near real-time processing. What I like most about Kira, it's about bringing operational simplicity created with the HPA, which is horizontal pod autoscaler, and works natively with Prometheus metrics. From an SRE perspective, it's a perfect balance of performance and cost efficiency scaling, not by guesswork, but by data. It's also highly observability friendly. You can actually trace auto scaling events alongside system metrics, which helps correlate scaling behavior with real user or batch load patterns. Next comes the service mesh integration. So this service mesh integration is one of the most transformative shifts in Kubernetes networking. As microservice grows, so does the complexity of managing communication, authentication, which retries encryption and observability. So a service mesh like Linkerd or Istio abstracts these concerns out of the application and handles them at the infrastructure layer. For example, by enabling MTLS, which is mutual TLS, we ensure secure service-to-service communication without changing a single line of code. From a reliability standpoint, service mesh gives you like powerful manageable circuit breaking, retrace with backup, and canary routing are all policy driven. Observability is another major advantage with built-in telemetry. We can trace latency per identity bottlenecks and detect cascading failures before they impact end users. So now let's see about the automated failure detection, like as we discussed, which is liveliness probes, readiness probes, container restart policy, and HPS scaling response. In the liveliness probes, which verifies the application health via HTTP endpoints, trigger container restarts for unresponsive services, set appropriate timeouts, and failure thresholds. Whereas in the readiness probes, use startup checks to remove unhealthy pods from service discovery until ready to serve traffic. Prevent routing requests to degraded instances. container restart policies. Utilize Kubernetes built-in restart mechanism with exponential backup for automatic recovery from transition failures, eliminating manual intervention. HPS scaling response. Configure horizontal code autoscaler policy to swiftly scale replicas based on CPU, memory, or custom metrics like as we discussed, the event hub, messages, queue depth, and processing lag. Observability with Prometheus and Grafana. So establishing the baselines for anomaly detection, which is establishing robust baselines of normal performance metrics, is crucial for identifying deviation that signal potential issues. Pay close attention to these critical indicators. One is message throughputs. Second one will be the consumer lag or QDAP. Third one will be the error rate thresholds. And the fourth one is resource utilization. Message throughput, which monitor volume and processing speed. Consumer lag, which tracks consumer delays and message queues. Error rate threshold, which define acceptable error rates and alert on breaches. Resource utilization, which observes CPU, memory, network, and disk usage for anomalies. This regularly update baselines for effective automated alerting and scaling discussions. When it comes to observability, so one of the biggest breakthroughs for me personally has been operationalizing observability, which is going beyond logs and metrics to actual actionable insight. For example, distributed tracing combined with real-time dashboards allows us to visualize transaction journeys end to end. Instead of treating incidents as isolated problems, we now view them as signals to improve system resilience. When observability is embedded into the platform from day one, mean time to detection and recovery drops dramatically, and engineers gain confidence in continuous delivery. Visual bottleneck identification, which is here we are using heat map analysis techniques. The harness Grafana's advanced visualizations to create comprehensive heat maps, pinpointing performance, bottlenecks, and capacity constraints across your streaming pipeline. The visually identity which processing, hotspots, and uneven load distribution, temporal patterns in across micro network and storage IO bottlenecks. The color-coded intensity maps provide intuitive understanding of system behavior, guiding optimization effort based on actual performance impact. So architecting resilience in this is the pattern catalog where we have modernized legacy ETL, build next-gen event platforms, and ensure SLA compliance. So when it comes to the resilience, so where the automation plays a huge role in us in achieving this zero downtime operation pipelines and progressive delivery techniques like Blue Tree and Canary Argo rollouts, which can control risk while maintaining velocity. But automation is not only about deployment; it's also about recovery, self-healing systems that restart pods, rotate secrets, or fail over seamlessly, having have become the foundation of reliability. The ultimate goal is to make failure routine predictable and recoverable so team can focus on innovation instead of firefighting. So the in the modernized legacy ETL, the transform traditional batch pipelines into resilient streaming architectures, leveraging event-driven patterns and cloud-native orchestration. Whereas in the build next-gen event platforms, architect self-healing, auto-scaling event-driven systems with comprehensive observability built in from day one. And in the ensure SLA compliance, we implement proactive monitoring and automated recovery to meet stringent availability and performance requirements for mission critical environments. So let's get into the architecting resilient streaming systems, which is like production ready patterns, automate with Kubernetes, comprehensive observability. The production ready patterns, which leverage proven design pattern for ready stream, circuit breakers, and deterministic replay strategies to mitigate real world failure scenarios. And in the automate with Kubernetes, which utilize liveliness probes, readiness checks, and HP policies to create self-healing systems, ensuring graceful recovery with minimal intervention. And in the comprehensive observability, which implement Prometheus and Grafana monitoring with metric baseline, lag detection, and visual heat maps to uphold SLA compliance in critical environments. So, as we look ahead, the future of SRE and Kubernetes is heading toward even greater abstraction as and in the serverless orchestration, policy-driven automation, and AI-assisted operations. The combination of AI-based anomaly detection with event-driven remediation will reshape how we approach reliability at scale. The next phase is not just about uptime, it's about the system intelligence, platforms that learn from incidents, predict degradation, and adapt autonomy. This is where the boundary between human insight and machine precision truly starts to blur. And so that's it. Thank you all for joining today. I hope this session gave you a practical view of how Kubernetes native design, automation, and observability can truly elevate reliability in modern cloud platforms. It's been great sharing my experience, and I would love to continue the conversation. Feel free to contact or reach out if you'd like to discuss resilience, engineering, or cloud native modernization further. Thank you again for your time. Thank you.